Hi guys. So I'm Fran Moore. I'm an assistant professor in environmental science and policy. Some of you guys know me, but a lot of you don't. So I am in the energy graduate group. So anyway, I'm here to introduce Steve Davis, who's coming from UC Irvine. I'm really excited to kind of welcome him here to Davis because Steve's work is kind of really amazing and kind of spanning this really broad swath in terms of kind of the human environment interaction space. So Steve actually has a law degree and practiced law for some years before taking a PhD in kind of geochemical geology from Stanford. And then since then, his work's kind of really expanded to think broadly kind of across social science, policy, engineering, and the environmental sciences to think about kind of human interactions with the environment. Just in terms of the range of things he works on, so today he's going to be talking about kind of zero carbon energy supply. But he also kind of just this week published a paper on the effects of climate change on beer supply and beer prices, which was picked up among other places by The Daily Show and Stephen Colbert's show. So I think that makes him one of the coolest people I know. So anyway, welcome Steve.
Thanks, Fran. And yeah, that's a flattering introduction. I'm very happy to be here. I worked with a few people at Davis, but never had the chance to come and visit. And I'm grateful to the energy group, who I think you guys sort of chose me, so I'm pretty flattered by that too. Maybe even more than The Daily Show, honestly. Okay, so the title here is a little different, I realize, than what I had posted, but it's basically the wonkier version of the sexy title that I put on the abstract that I sent you guys, which is, how do we get to a net zero emissions energy system? So I'm going to talk about 3 distinct projects that I've worked on and that have all been published in the last year, which relate to different aspects of this. And one is actually a review paper that sort of scopes the entire ideas behind what a net zero emissions energy system might look like. So just by way of background, because I never know exactly who I'm talking to, this is a plot from the last AR of the IPCC, so one that maybe you've already seen, but what it shows on the x-axis is cumulative CO2 emissions since the pre-industrial era, and on the y-axis the temperature anomaly since the pre-industrial. And what you're meant to see, there is a cone of uncertainty there, but really what you see is that these lines are lines. They're not really curves. It's a linear relationship. And that's the sort of underpinning of all of the work that you may be familiar with on carbon budgets. The idea is that every molecule of CO2 that we add to the atmosphere is essentially another little increment on the global thermostat, and at least over timescales that humans are today concerned about, that's a linear relationship. So what that means is if we want to actually stabilize the global climate, we need to figure out how to get to zero emissions. So this is by way of explaining why we're even talking about near zero emission or net zero emissions. So if I plot, for instance, on the same x-axis here, the proven reserves of fossil fuels around the world and broken out into some different types, you can see that we've got plenty of these fuels available to get us towards 4 degrees of warming. And I'm sure everyone knows that the target is 1.5 or 2, depending on who you ask. Now, mind you, these are proven reserves, which mean they're economic at today's prices. So resources are vastly bigger. This is what we could actually make a profit by getting out of the ground. So I like to talk to students about this, and I'm sort of obsessed with food, I guess. I talk about it as a cookie jar problem. So these fossil fuels are effectively cookies in a jar. They're attractive. Really, you want to get them out and use them. But we have to, if we want to stabilize the climate, walk past that cookie jar for the rest of human civilization and not dip our hands in, right? So that's a big problem, and that's why we're interested in how do we do that and not sacrifice our well-being. So another way of looking at this, just a few plots to show you some simulations that we've done looking at what happened if we instantaneously stabilized anthropogenic CO2 emissions at different levels. So this plot's showing you annual CO2 emissions from the pre-industrial era through, I think it's about 2015 is the data on here. And then we just instantaneously bring those to different levels of CO2. So these are in petagrams of carbon. So you'd have to multiply times the 3.67 to get the gigatons of CO2. But the point is that at these different levels, we actually see the atmospheric CO2 continues to increase in all but, of course, the one where we've completely zeroed out, which is the black line on here. So all of these other ones, the concentrations, even at less than 4 gigatons of CO2 emissions per year, the CO2 concentrations in the atmosphere continue to increase. And of course, we know because of that previous plot that I showed you on the first slide that means we're going to get an increase in temperature. So if you're, for instance, wanting to stabilize the climate below 2 degrees, this really shows you that you have to get to extremely low levels of CO2 emissions, near zero, if not zero, to do that. And so this is obviously a very long time scale, and you can delay the point at which you cross over 2 degrees of warming, but even at a level of 3.5 or so gigatons of CO2 per year, you still cross 2 degrees in the next couple hundred years. All right. So the other thing that I wanted to mention by way of background, I'm going to spend most of my time today talking about things that are really difficult to decarbonize, and I'm going to make it sound trivial to decarbonize the rest, which I think a lot of you realize that's not at all the case. But I do want to say, and Alyssa and I have had a nice conversation this morning, that, you know, even in the last 5 to 10 years, we've seen a lot of progress on things, and I'm much more optimistic about our ability to decrease emissions from the electricity sector, for instance, or light-duty vehicles than I was 5 or 6 years ago. So solar panels, wind, hydroelectricity, electric vehicles, probably some of you know much more about the details of these different technologies than even I do, but I think these are all things that I'm optimistic about. I see the prices tending to come down. There's increased penetration in a lot of these different technologies, and there are ways that I think we could conceivably decrease our emissions from light-duty travel and electricity to near zero. So what am I really talking about then? I'm talking about the more difficult things as I perceive them to decarbonize. So I'm going to bend those into 3 big categories. The first being aviation and long-distance transport, and I'll get into the details of why I think these are hard in a second. The other one I'll talk about a bit today is industrial materials. We have a lot of CO2 emissions coming from things like cement and steel, and we'll talk about why those are particularly difficult to get rid of. And finally, a really highly reliable electricity system that's based on some of those variable sources of electricity may be particularly challenging, and we'll talk about that. So how much of these difficult emissions are we talking about? This is from the review paper I mentioned that we had earlier this year. And the pie is showing you in these exploded out sections of the pie those fractions of our emissions that we think are in these very difficult to decarbonize categories. And to some extent, we had to kind of make some loose assumptions. So for instance, it's not really well known how much CO2 is coming from load following electricity around the world. We ended up looking at, in the US, the minimum monthly electricity demand, and we assumed everything in excess of that was effectively having to follow load, and we used the ratio in the US to estimate the global. So admittedly, that's an imperfect way of estimating it, but nonetheless, you see that the amount of electricity generation that's following variable loads might be on the order of 10 or 12%. Also there in the orange exploded pieces are those portions of transportation emissions that I'm going to tell you I think are hard. Aviation, ocean shipping, and long-distance road transport. Now, mind you, the ones that aren't exploded, now remember I said I'm going to pretend like those are trivial or at least easy to do or possible to do. We could have debates and conversations about why those are not so easy, of course. But for the sake of the talk today, I'm kind of operating under this heroic assumption that we'll successfully be able to electrify, for instance, or use fuel cells or something for the light-duty vehicles. The other ones, the industrial materials that I mentioned, iron and steel and cement. The ones that I have on here, this 5% for the iron and steel and 4% for cement, those are just the process emissions. So not the heat if it's being generated with fossil fuels. And we'll talk about that more in a minute if you're not clear what that is. So if you just tally up those difficult pieces of the pie, what you see is that it's roughly 9 billion of the 34 billion tons of carbon that we emitted in 2014. So more than a quarter of global emissions are in these really difficult categories. So all of this, you should be thinking, okay, we need to get to zero for stabilizing the climate. we've got a lot of work to do on what I'm calling the easy things, and we have more than a quarter of the pie that's in the really difficult things. So that's the point of this, is to start thinking sort of futuristically about if we're going to deploy systems that can make steel and cement or follow electricity demand without emitting CO2, we need to start thinking about how those things are going to work now, because we don't have that long, actually, to reduce emissions and stabilize the climate. Yeah. Sure. Yeah, well, so, I mean, it depends on what your climate target that you're shooting for is, but if you wanted to actually meet the sort of 2-degree target, for instance, we'd be thinking about almost the whole pie needs to be accomplished by certainly the end of the century, if not mid-century. So we don't have a lot of time, yeah. Any other questions? Okay. The other thing I wanted to mention is some other work that I've done on what I call infrastructural inertia. So all of the things around the world that emit CO2, turns out these are long-lived assets, power plants being something you could think of. And so even if we stopped building new ones today and let the existing ones operate over their expected economic lifetimes, we would still be dealing with a lot of CO2 emissions. So this was a paper we published back in 2010 that estimated at that time about 500 billion tons of CO2 were locked in based on those existing energy assets. Of course, we could retire those things early, prematurely, but that would have a cost as well that we would have to contend with. So all of this is to say, and it gets to the time question, if we wanted to actually decarbonize our energy system to the point of reaching a 2-degree target, we really need to be working on these things now. It's not a problem that we can get to once we figure out the light duty or the electricity. We need to figure out how to do these difficult things in the near term as well. Okay, so first off, we're going to start on the fuels, the transport and aviation. And I want to talk just briefly about energy density. I think this will be review for a lot of you, but it's kind of fun. So dry wood has about 17 megajoules per kilogram of dry wood. It's just some facts here. Coal, you're up into the 20s. And of course, refined oil products like gasoline, you're already into the 40s of megajoules per kilogram. So I like to say that just looking at those numbers, you have a pretty good sense of why we don't have wood-powered cars. Like, you can get a lot further, and it's a lot easier to fill your tank with those liquid refined oil products. Anyone know offhand or want to guess what the energy density of your laptop battery is? Yeah, it's less than 1. So definitely this is one of the reasons that it's challenging to have battery electric vehicles. So you might say, well, what about gas? Gas certainly has a lot of energy for unit mass. So hydrogen is about 143, but of course it being a gas, the energy density by unit volume is dramatically less. And so if you compare that to jet fuel that we use, the volume has about 3,000 plus times more energy. So this explains a lot about why we have liquid fuels for aviation as well. And so I think when you're dealing with something like an airplane, understanding that you really want those super energy dense liquid fuels to run a plane is really important. And it's sort of grounded in those physics that we just went over. There are people playing with how to electrify or even run a plane on hydrogen, but those are really experimental, like single-person planes that are a little iffy already. The idea that we're going to fly a jumbo jet across the Atlantic on hydrogen at any time in the near term, I would call very far-fetched. Similarly, I had put shipping into the category of difficult to decarbonize emissions, and I think we all know now that global trade is really reliant on these kinds of container ships that can relatively cheaply travel across the oceans. Now, there are also companies looking at how to run these type of ships on hydrogen and other sources that aren't fossil fuels. But again, I think the energy density is really important, and the affordability of those other options is still in question, at least in the near term. But maybe the one that I think is most interesting is to think about Class 8 trucks like this semi here, and knowing that these things can often have a range of 1,000 miles on a fill-up of fuel. So for instance, if we wanted to electrify these, you can do some back-of-envelope calculations to figure out at the lithium-ion battery energy density that I quoted, and figuring out the volume of those closely packed cells that they use in like Teslas, it would take up about a third of the volume of this truck in batteries to get the same range as a diesel-powered truck, and probably about 40% of its payload capacity. So you might say, okay, well, we'll take up 40%, but at that point, you're hauling batteries around the country as much as you're hauling stuff. So it's definitely a consideration, and I think it's one thing to say that we might electrify around town transport or short haul, medium duty trucks, but when you're talking about something, if you want the long range, and it could be too that maybe we change the way we do things. You guys are probably up on this, some of you, modal shifts or interchangeable batteries, different ways of doing it. Maybe these become autonomous and we have like fleets of trucks that are sort of stopping in and charging. Who knows what the future holds? But if we wanted to maintain the current regime of trucks that can go 1,000 miles, it doesn't look like batteries are a really good option, at least in the near term. Hydrogen's not that much different, actually. So if you wanted to do these with fuel cells, it's a little better. Maybe 10% of the payload volume is a bigger concern, depending on the pressure of the hydrogen system. Maybe it's 20% of the payload capacity. So at bigger pressure vessels, you tend to have more of a mass of the pressure vessel itself, or if you have cryogenic systems, they have a mass associated with keeping the hydrogen cold. And so, again, long-haul trucking with these alternative technologies is still a work in progress. So all of this is to say that if we want high energy density liquid fuels that don't add CO2 to the atmosphere, how do we do that? So I'm going to start building this schematic that comes from our review paper, and I'll have it reoccur throughout the talk. But here I've got these little cartoon sketches of a plane and a truck, and we want to give them, at least in these purple lines, some hydrocarbons, high energy density. Where do those come from if they're carbon neutral? Well, it could be biofuels, and I think that's something that I know folks here at Davis study a lot. And there may be ways to make those low or near zero carbon. You could also imagine synthesizing your own hydrocarbons. If you did it with, of course, both of these solutions would require zero emissions electricity inputs, as well as if you're synthesizing your own, you need hydrogen, and you don't need that to be from reformed natural gas. You need it to be from a renewable, sort of non-emitting source. So maybe you're electrolyzing water with your zero carbon electricity. So that's the source of hydrogen if you want to synthesize a zero carbon fuel. And to get the carbon in there, maybe you're capturing that from the atmosphere. You might be getting it from biofuels. You can sort of synthesize enhanced biofuels, so add extra energy in there. And I'll mention something here, and we'll discuss it more later. Maybe you're also able to get some carbon from capturing process emissions from cement. I'll say more about that in a bit. The other option, just for the sake of completeness, of course, you could imagine maybe driving some trucks or planes directly on hydrogen. So I do have a blue arrow going there. The other thing, for the sake of completeness, is if you're electrolyzing hydrogen with a zero emissions energy source, you could make ammonia. And some of you may know that there are actually engines that can thermally decompose ammonia and run directly on ammonia. And since there's no carbon there, you're not adding carbon to the atmosphere. Apparently there's some farm equipment that runs on this in the US. I learned this in writing the paper. I didn't know that. So those, I think, are the main options. The last one I'll just put on the schematic. I think, again, this is a further in the future prospect, but folks working on direct solar fuels. So essentially artificial photosynthesis that could generate a hydrocarbon directly from the sunlight. And that's an emerging area of research. So what's the problem? If we want to synthesize these high energy density but no emission carbon fuels, I told you about electrolysis was kind of at the core of a couple of those approaches. What you're seeing here is a plot of the cost of hydrogen on these contours as a function of electricity costs on the x-axis and the capital cost of the electrolyzer on the y-axis. And just for the sake of comparison, I've drawn on in this line where the cost of current methane-derived hydrogen, which is the way we get most of our hydrogen, if you didn't know. It's about $1.50 a kilogram. So you may already kind of have this in mind, but that dot right there is basically where we're at in terms of the cost of an electrolyzer and typical electricity costs. So closer to $5 a kilogram, so almost a factor of 5 more expensive than the methane-derived hydrogen. So this is already starting to give you a sense of if you want to synthesize a zero-carbon hydrocarbon and you're going to do it with electrolysis, it's going to be more expensive than going the fossil fuel route. And that's maybe something we're okay with, but if we wanted to try to be the economical people that we all are and get to the same price, we got to get the cost of this hydrogen down. So I'm going to wrap up this little part on the aviation and long-distance transport by summarizing that I think, at least, and we could have a debate maybe, that high-energy density liquid fuels are probably going to be necessary for these parts of the transportation system for, as far as I can see, decades to come. I think the currently available options that we have for making such near zero or net zero emissions fuels are currently too costly, and they should be a focus of research. In particular, as I've highlighted, I think electrolysis needs to get cheaper, and that should be a real priority for reasons in addition of helping to integrate the energy system, which I'll mention at the end. Yeah. Sure. Yeah, so the oldest technology is the one based on alkalins, and it's actually a pretty large-scale production process, but it's the cheapest that we have, I think, but it's also hasn't really decreased in price, and it's been a known technology for several decades now. There's other newer electrolyzers like PEM. I don't know if you're an electrolyzer person. So they function more dynamically, and there's also like molten carbonate processes that might be brought to bear. So there are different avenues that people are working on, and you could ask different experts how quickly they think the prices could come down. There are people that argue that we might be able to cut those electrolysis costs by half in the next few decades, maybe even more, but who knows? I think it's one of these things we haven't really probably given it the effort that we could, because we've had this cheap source from fossil methane. Yeah. Sure. Well, so I have kind of calculated if we were able to capture carbon for about $100 a ton, and at the current cost of electrolysis, what kind of a price on carbon we would need to have economic equality with fossil fuels, and it's around $350 a ton of CO2. So I don't know if that completely answers your question, but there are two axes here. My arrow wasn't meant to imply that I think that's the pathway necessarily. It could be that we're able to, by integrating different parts of the energy system, maybe really decrease our electricity costs, and even if electrolysis doesn't get substantially cheaper, be more competitive. Okay, so turning to the industrial materials, let's start by talking about cement, something I know Alyssa is interested in, and maybe some others of you. So about 8% of global CO2 emissions come from manufacturing cements, around 2.5 billion tons in 2014. You may recall on my pie chart I had 4%. Well, that's because there's two sources of CO2 from cement. So this is just a real basic schematic of what a cement kiln looks like. They dump limestone in the top, and round about here in the kiln it gets to 1,400, 1,500 degrees C, so very hot. And the process is this calcination, so we're effectively driving off CO2 and leaving us with the lime that's like the special sauce of cement. And so the two sources of CO2 then, about half, is because of this calcination process. So it's fundamental to the making of the lime that we get that attendant emission of CO2. And the other half is to get that super high temperature, and so that's typically done with fossil fuels, and these are the two main sources of the CO2. So when I had 4% on my pie chart, I was assuming that we're going to get rid of this. We're going to maybe electrify or come up with some way of generating that high heat that doesn't emit CO2. And I was leaving as the more difficult part these process emissions. So how do we get around this? If we want cement, which I think there's very few people that think we're going to walk away from one of the most important structural materials of our society. So how do we do that? Steel is a similar situation. It's actually a little more complex. In this schematic of a blast furnace, you can sort of see they've got this molten iron ore here, and they dump in coking coal. The coking coal, it's a little more complex, I said, because the coal actually burns to some extent in that molten mix. So it actually heats the mix from the inside, but also the carbon in the coal acts to reduce the iron ore and make it ready for steel. So it's sort of having a dual purpose. Also, the carbon that's present in the resulting steel lends some material properties to the steel. It helps it be stronger. And so to change this process and not have coking coal be involved would have potentially effects on the materials quality, and it's not clear exactly how we would do it. So one suggestion that people sometimes talk about is by using hydrogen as a reductant instead of carbon. And people have actually done some demonstrations that this is possible, but it's not something that we're doing at large scale yet. So I did mention here in red that about a quarter of current emissions from iron and steel processing could be avoided if we electrified and started doing recycling, but we don't think we're able to do that to meet all of the demand. There's not enough scrap metal being produced to actually meet current demand, so we still have to do some of this sort of virgin processing of iron. Okay, so how do we do that? I've added on the schematic the demand for industrial materials there in the upper part, and this is sort of my cement and steel kiln here. And so I've got the green line from some sort of no carbon electricity is going in there. The main way people talk about, like I already mentioned, is in the steel process, maybe using hydrogen. But more often what people talk about for both of these processes is carbon capture and storage. And so that's definitely something that we know how to do. In many cases, it might be easier at a cement kiln than even a power plant because the streams of CO2 that are being produced are more pure. The problem, of course, is that we have a lot of cement kilns already in existence. They live a long time. They are leaky, they rotate, and they're at 1,500 degrees C. So the idea of like retrofitting something to capture CO2 emanating from that kiln is pretty tricky. And the last thing I'll say about the industrial materials is that these are probably, we like the fact that they're very conservative industries. And when I say conservative, I'm not talking about politics. I'm talking about they're holding up bridges and skyscrapers. And so the idea of like, let's play with the recipe and see what we can do, people are generally not too keen on that because there's real safety concerns. And we've got recipes that work. So there are options here, and folks like Alyssa, I think, have worked on some alternative mixes of cements, and Sabby Miller as well in your group. So that's an option, but right now most times people are talking about carbon capture and storage. And that's the storage piece. Okay, so I want to spend a little bit of time explaining a study that we did a couple years ago about cement. And these process cement emissions over time, this is global fluxes of those process emissions, and you can see they've been increasing exponentially as we've been building more and more stuff with cement. So I was interested in this because it's often listed in the carbon budgets as a big source, and some of us were understanding that there's also a reverse process that structural engineers have known about for a long time called carbonation. And so effectively this is the reversal of that calcination process that after you put lime in cement, in the presence of ambient CO2 and water, it actually starts reabsorbing some of the CO2 and turning back into calcium carbonate. And the reason structural engineers are interested in this is that it affects the structural properties of the cement. As I understand it, it changes the pH actually and can lead to oxidation of some of the reinforcing metals. So it's generally regarded as a bad thing, something that happens during the aging of cement materials that we want to avoid. So there's a lot of effort that gets put into coating cements and trying to resist this process. But as you can see, it's sucking up CO2 from the air. So the carbon cycle scientist in me is like, hey, great, right? So what we wanted to know is how much of this is going on with all the cements that exist in our society. How big is this flux of CO2 going into cement materials? And it's a highly uncertain process, but we modeled it based on fixed diffusion law, which is a relatively simple diffusion equation where you have the depth of the carbonation from a surface as a function of the square root of time and different rate coefficients. And I only show one on here, but you can imagine there's a lot of different things that might mediate the rate of this carbonation. So just for an example, if this is a chunk of cement material, obviously the CO2 is being absorbed from the outside in, and what you're seeing on this line graph is the depth of that carbonation over time. So the first part of that curve, the blue, is sort of reflecting after a demolition of a building or of a road or something, you've got this particles of cement and they're absorbing CO2. But at some point, there may be a decision to be made about how to dispose of those pieces of cement. A lot of it actually ends up being buried in landfills, and that's the red line. You see that because it reduces the amount of interaction with the atmosphere, maybe also interaction with water, it tends to slow this carbonation process down, as opposed to maybe disposing of it somewhere in the open air, or often it gets recycled as roadbed material. So we looked at this, and we actually looked at 26 different factors in the rate of this carbonation, and we did a Monte Carlo uncertainty analysis where we took ranges for all of these different factors from the literature, and we varied them randomly in a few thousand simulations. And what we ended up finding was an estimate of the global uptake of CO2 by cement materials over time. And you see the uncertainty bounds on here in green. But the net then turns out to be substantially less than the total process emission that often gets quoted. And so actually in recent years, we think on the order of about 40-45% of these process emissions is actually being reabsorbed by older cements already in existence. And so sometimes I've explained this as it's a little bit like bioenergy. So you have a tree, you cut it down and burn it. You get CO2 from the tree, but if you allow a new tree to grow, then it's sucking up some of that CO2 over time. It's sort of similar with cement. You make cement from limestone, you get a CO2 process emission, but then over the lifetime of that cement, it's reabsorbing at least some of that CO2. So this actually kind of leads me to, well, I won't jump ahead. There's a couple more plots here. So this is actually showing the different types of cement materials that we looked at. Something interesting is that cement used in mortars turns out to be, in our estimates, a larger source of carbonation than some of the others. It tends to have more lime in the mix, which is what's doing the absorbing. And it's often what gets used on the outside of buildings, like as surfaces. So it actually, although it's not the largest use of cement, it is a disproportionately large source of the carbonation. So this is what I was going to say. I think what this ends up making me think is that as between fossil fuel combustion CO2 and process emissions from cement, we should be prioritizing the fossil fuel emissions, because at least the cement is going to suck back up some of that CO2 over its life. Not to say we shouldn't do both, mind you. The other thing it makes me think is we should be thinking a little more carefully about how we're disposing of cement materials, and where possible to recycle those and leave them out in an open air environment where this process can happen faster would be a good idea. And finally, something that occurred to us in writing this is if we were successful in putting CCS technologies on a cement kiln and storing those out of the atmosphere, then the CO2 that gets taken up during the carbonation process is a negative emission. So this is when I said maybe we could synthesize fuels with CO2 from cement. That's another angle where if you believe that the carbonation is going to help out, those could be thought of a little bit like a biofuel or something like that, where maybe over the long haul it might equalize. Any questions on this? Yeah.
I have a thought.
Sure.
What if you put it in the ocean?
That's a great idea. Actually, I've been asked that before in giving this talk, and I have to admit I haven't fully looked into it, but I'm not sure how the carbonation process happens underwater, if it's enhanced or not. There's probably better chemists in the room that could think about that, but I think it's not a crazy idea and should be looked into. Maybe you could write that paper. Yeah. Yeah. Well, so I think it is mostly about the concentration of CO2 that it's being exposed to, and I think CO2 is pretty well mixed, and if anything, at higher altitudes, it'd be less pressure, so probably less uptake of CO2. But I think you guys are on the right track of like, let's think about, as my third bullet says, how are we disposing of these cement materials, and is there a way we can do that in a smarter way to accelerate this process? Yeah, I mean, it's just like the original limestone, so it could be weathered, I suppose, but you know, it's a pretty stable mineral. Yeah.
There's to like proposed direct air capture, like experimental.
Like cost-wise, you mean?
Just in terms of like how quickly it takes up the carbon.
Yeah, I mean, that's the downside of this. We're talking about decades, you know. So those large recent year uptakes, actually a fair bit of that is in like the first couple of years that it's exposed, but it diminishes in like as a decaying, the square root of time. So after you get that first layer carbonated, it takes progressively longer to get deeper. And so the large amount of carbonation in recent years, it's mostly because we've built a lot of new cement in recent years. So it's going to take a long time to fully absorb all of that. So maybe the ocean or some of these other ideas is a good one. And of course there's, you know, if you could grind it up into smaller bits, that would help. But there's energy inputs there to consider, and so, you know, trade-offs that we didn't really look at. Else? Yeah. Yeah, I mean, I'm not an expert in this. We had a guy on our paper that is at Imperial College named Paul Fennell, but I am aware there's a lot of literature about CCS in cement, and I'm certain that there's been demonstrations of new kilns that have CCS. So it is something people are looking at because they know this is a tough one to get rid of. Yeah? Yeah, so that's what I was saying, that in recent years, the uptake is about 45% of the process emissions, but that's not looking at the same CO2. So it's around 3 or 4 decades, depending on the environment, to fully absorb the CO2 that's produced if it's kind of managed in a way that it's out in the open air. Does that answer your question? All right, I'm going to move on to the maybe people's favorite, the reliability of electricity. So this is something I know a lot of you are interested in. You know, we've got the solar and wind down here. These are nice carbon-free sources of electricity. How do we manage our demands in time with these variable inputs? And so I'm going to tell you why I think this is a challenge. And so I've got a hospital on here to reflect the demand for reliable electricity. So I think there's really 3 major ways we could think about this. There's flexible generation sources, which these are not. There's demand management, so maybe we are actually a little bit flexible on when we're demanding the electricity. And of course, then there's energy storage options. And some combination of those is how we can make our electricity sector reliable. And so I've added a couple things on here, some amorphous centralized energy storage, whether that's batteries or some thermal storage. Compressed air storage, and we already had pumped storage associated with the hydropower. So this is a study that we published earlier this year. It's not the sort of detailed, sophisticated dispatch modeling that some of you may do. What we did was we looked at 36 years of reanalysis data over the United States. And so the reanalysis data product we use is from NASA's MERA-2. It's about a half-degree resolution. And what we were interested in is if we took this kind of geophysical constraint of how much sunlight is hitting the surface of the United States and how much wind is incident at the surface of the United States, how variable is that over time, and how does the variability of that reconcile with the variability of our demand? So what you're looking at here is all 36 years of data plotted by month of year. The purple is the wind. So just in general, some of you probably already know that wind tends to be more of a source in the wintertime, and it drops off and lulls in the summer. But you also see a lot of spikes in the wind. So it's very variable throughout the year. In contrast, the yellow is the solar, which is sort of nicely the opposite. It tends to peak during the longer summer days. And the variability around that, if you can make it out, is a lot less. The orange line on here is actually just 1 year of electricity demand in the United States, and all this is normalized by the mean for our 36-year period. So it's just meant to give you a flavor of how the modes of variability are differing. You could also look at this in terms of the hours of the day in the summer and winter, and of course we all know that the sun has this tendency of going down in the evening. So you get more sunlight in the middle of the day in the summer, and then you're seeing that on these. You also get more wind, but also still a substantial variability in the wintertime. And what you may be able to make out is that wind is slightly more likely to be a presence at nighttime, actually, in the U.S. So what we were interested in is, given those sort of, like I said, geophysical inputs, how does that really mediate the reliability of our electricity system if we wanted to try to get all of our electricity from just solar and wind? So that was kind of the premise. And I should back up and say part of the motivation for this was looking at some of the studies that have used sophisticated modeling to come up with what would be the cost of trying to get a lot of solar and wind into our energy system. They tend to see that you could get to maybe 80% of our electricity coming from solar and wind at pretty affordable prices. And then beyond that, costs seem to increase pretty substantially. And we wanted to understand, because all those are done with these sort of black box models, or at least very, very sophisticated models that are hard to really understand, if we looked at it in a very simplistic way, is there some geophysical explanation for why that 80% is an inflection point? So what I'm showing you here, there's going to be 4 of these, but I wanted to introduce them one at a time so as to not overwhelm you. The vertical axis here is showing what mix of solar and wind we have. So on the bottom is a 100% wind system, top is 100% solar, and then gradations in between. On the horizontal axis, what we're looking at is the effect of area. So on the left side, the DC is the Washington, D.C., that area, on up to New Hampshire, New York, California, the Western Interconnect, or the entire continental United States on the right side. And so what you see here is that obviously in a situation where we have no storage, that's what this is, and 1x generation means that we've built exactly the amount of solar and wind to meet the integrated demand over the year in the US. So we haven't overbuilt at all. What we get is the exact amount of energy, obviously not necessarily at the same time, but it is the same amount of generation. And so what we see is that in this situation, the favorable mix seems to be about 3-to-1 wind to solar. And of course, with the wind, the more you spread that out, the more reliable it becomes. And we could maybe get to 75% of our demand being met by solar and wind under this situation. So not great. Does anyone know, you probably do, but what sort of reliability do we demand of our electricity system in this country by statute? It's 99.98%. So 75% is not quite going to cut it. But so let's continue. Did someone have a question? Yeah. Yeah, well, I should be clear then. So what this is saying is that, if you add up total electricity demand in the U.S. over a year, and we build solar and wind that can produce that amount of electricity exactly, but not necessarily in time, how much of the time does that solar and wind meet our demand, and how much does it not? So the 75% that's the amount of time that our demands are covered. So there's a gap of maybe 25% of the time under that scenario where we're not getting the electricity we need. Yeah.
And for the horizontal axis, it's basically saying like if you have a 10 square mile area versus like California-sized area versus a whole continent.
Exactly, right. So, and you guys probably know this, the more you distribute these generating assets in space, you have less variability because it's not one space you're dealing with. You can kind of balance across the area. So, yeah.
What's the assumption for regional interconnection?
It's a copper plate assumption with zero electricity loss. So I said simple. So we're basically saying if solar is being produced then in Wyoming, then someone in California can get it instantly with no electricity loss. So yeah, not a realistic assumption, but again, we're just trying to understand how the geophysical constraints are playing here. So if we add to this a scenario where we have 12 hours of mean electricity storage, what you see is a pretty interesting shift towards solar, and that makes sense. We have to overcome the diurnal variability of solar, and 12 hours is just the right amount. So we actually get more of a 3-to-1 solar to wind mix in this case, and the reliability increases. You'll also notice that the spatial dimension matters less in the greater solar scenario. So you see those reliabilities even over areas as small as New Hampshire. So 85% of the time maybe our electricity demands could be met. And that's with 12 hours of storage. So if we go back to a no storage, but in this case we're overbuilding by 50%. So the total generation is 150% of our total demand over the year. This is often discussed as a way out of we can build excess assets to cover us when stuff goes away. Again, because we don't have storage, we're back down to a wind-heavy mix, but the reliability does increase. So you see up to 85 or even 90% of the time. And then finally, the sort of case where we've overbuilt, if you will, by 50%, and we've got 12 hours of storage. Now we're starting to get into some pretty high levels of reliability, maybe into the 99% range. So to look at this a little differently, again, this goes from an all wind to an all solar and the mixes that you see in between. And what I'm doing here is showing the fraction of time that demand is being met by solar, wind, and our hypothetical storage. The black is with no storage, and the different greens are showing 12 hours of storage, 4 days of storage, or 32 days of storage. And so what you're meant to kind of note here is that to get to 80%, you can actually do it with wind with almost no storage. With solar, you can do it with 12 hours of storage. So this is starting to tell us why these studies have shown that maybe you could economically get to the 80% mark, but afterwards, as we move towards 100%, you can see the exponential increase in the amount of generation that we need if you're overbuilding and or the amount of storage that you want. By the way, 12 hours of storage, I'm saying that like, yeah, no problem. Does anyone have a sense of like 12 hours of mean demand of storage in the U.S. is, I think it's 5.4 terawatt hours. It's 150 years of production at Tesla's Gigafactory. So it's not an incidental amount of storage. But yeah.
And your assumption for storage is also ideal.
Yeah. Just in keeping with the dead simple approach that we're using. That's right. So we can also plot this at we can also kind of look at it on a logarithmic scale to see what happens at that upper end. And I don't actually like this axis very much. You should focus on this is the how much we're overbuilding axis on the left. It applies here too. And you can kind of see that as we really get to those high levels of reliability, you really have to have a lot. Like these are the dark green lines are the 32 days of storage lines. So those are starting to give you some idea of the magnitude of storage that would be necessary if we wanted to do this with storage and not flexible generation or demand management, the other options I mentioned. Okay. Sorry, I had too many animation. Yeah. Yeah, it's basically just a logarithmic axis, so you can see what's going on in these parts of the plots, especially as you get to the, I told you sort of the place we want to get is almost at the right side of this plot. So to see how that works without building 4 times as many wind turbines as we actually need most of the time, you need a lot of storage in those situations. And it's different, of course, at different mixes.
What's wrong with building 4 times?
Well, first off, it's expensive. I mean, it'd be like saying if you had a car that started 1 in every 6 days, you should buy 6 cars. It's like, really? That doesn't seem like the cheapest way out. I mean, this doesn't look at economics at all, but intuitively it tells me that maybe there's cheaper approaches to solving the problem.
I was just kind of curious.
Yeah, I mean, this doesn't include that, right?
Versus what do you end up with?
Yeah, I mean, I think, well, the shape of these sort of exponential increases sort of suggests to me that as we try to do everything with solar and wind, it gets crazy a little bit. And maybe that we have some flexible generation to back us up of some other sort. It doesn't have to be an emitting technology, obviously, but something that can help fill in those gaps. Probably is going to be cheaper than building 4 times as many wind turbines. But, that's something that it's a topic of research. So, yeah. Okay. So just to dig in, this is actually showing hourly data for the entire 36-year data set that we have over the months of the year. And the colors on here are showing you the reliability, so the percent of the time that demand is being met. The darker colors are lower reliability. And this is a scenario where we've got 75% of the generation from solar, 25% from wind, and we've only built exactly the amount that we need in the aggregate for the year with no storage. And you see it's only 62% reliable on average over this record. Just to zoom in on 1 week in December, those red hatched areas are the unmet demand. So we see solar coming in and out, and wind is just not enough to fill in the gaps and meet our demand. So that's kind of what it looks like. And if we add to that and we look, okay, same mix of solar and wind, but here we've overbuilt by 50% and we've got 12 hours of storage. A lot of increase in reliability, almost 99%. But again, looking at that same week, in this case we see the charging and discharging in green of our hypothetical storage, and we still see, in this case, a 5-day period when a large fraction of our demand is not being met, even in this 99% reliable case. So I think this is one of the most telling findings of this, because it starts to explain that this is not something that 12 hours of battery is going to help you out with. We're talking about 5 days in a row where 80% of our demand maybe isn't getting met. The magnitude of that gap in terms of not just the total power, but the duration of it on a successive day period starts to be really challenging to imagine building sufficient batteries. So, or pump storage or anything for that matter. Yeah. Yeah, so this is a dominantly solar mix, and so solar is worse in the wintertime. And so there's still going to be gaps in the wind in the wintertime as well, and when you don't have the solar, because it's a shorter day, then you run into problems. That's where you see those wintertime outages, basically. Yeah? The next slide shows the reverse, so I'll get to the wind-heavy scenario. But you're right. I think we're trying to be equal opportunity. A lot of people are excited about solar, and there's actually, some people will tell you there's concentrated areas where there's really good wind resources. Those are sort of diminishing in some cases. So the idea that we would have a solar-heavy system going forward doesn't seem that far-fetched. But yeah. Yeah, so that could be what the storage here is. We haven't really specified a technology, and I actually see where you're headed with that, and I kind of agree that a power to gas to power situation is probably more attractive than imagining lithium-ion batteries or something like that. So. those don't mix, right? Yeah, I agree. Okay, so this is, as promised, the scenario of a more wind-heavy mix. Again, no storage and just 1x generation. And you see here, the wind is worse in the summertime. So that's where most of the unreliability happens. And pulling out another week, we see a similar situation where there's days on end where you don't have enough. When we add the overbuilding and some storage, we get, again, a pretty high level of reliability. Still, most of the problems happen in the wind-heavy case during the summer, and still we can find these weeks where there's day after day of substantial shortfalls in our generation. So the takeaways from this study to me are that it's the geophysical variability of these resources can go a long way to understanding why an 80% threshold for energy or power demand from those solar and wind resources might be pretty feasible, but that going beyond that to very high levels of reliability becomes increasingly challenging. As I've mentioned a couple times, I'm beating you over the head a little bit, the gaps in the power production are not just a few hours, they tend to be large and long term. So you're talking about thousands of gigawatt hours or tens of petajoules if you prefer over several days. And that's where something like hydrogen starts to look a lot better than a short-term solution like batteries. The other thing that I didn't actually highlight is that it actually seems like it's maybe wasteful to pursue something that integrates large areas and sort of has as a mindset that we're going to go down the wind path versus something that where we're really investing in storage and kind of assuming we're going to be on a more solar path. I think this is kind of an interesting finding as well because it kind of seems like maybe we should be picking a horse, maybe to your point, of whether we think it's going to be solar dominant or wind dominant, because we don't want to build a lot of storage and a lot of transmission. It doesn't actually get us the reliability gain that we would get by pursuing one or the other of those technologies and going full bore. So, yeah. Yeah, that's a great point. So that's something that obviously our retrospective analysis has no insight on. It doesn't seem like there's very much trend visible, at least to this point. There have been, in the climate modeling community, studies of increased stagnation events, things like that. It's probably not too big a difference on the insolation, but the wind is where you might worry. And I honestly don't have a lot of insight on that, but it's a good question. Yeah, so I was going to mention that here at the end, but I think that the problem for demand management is really this second bullet here. So demand management is really useful if you want to shift loads or shave peaks during the day, but you're not going to get someone to turn off their refrigerator for a week or something like that. And really, when you start thinking about the magnitude of the energy demand that would need to be curtailed, it's going to necessitate like industrial production facilities because it's not going to, the sort of household use is not going to add up to that fraction of our electricity demand. And when you start thinking about curtailing large industrial uses of electricity, the cost of that is probably comparable to the cost of building new storage. So I think demand management has a role in the future in the flexibility of the electricity system, but I don't think it's going to overcome this kind of days-long 50% of our power demand variability. Yeah.
But if you're talking about synthesizing or electrolyzing all of our hydrocarbon fuel, that's going to be a huge energy demand.
I like where your head's at. Yeah, so that's one of the final points of all of this is that by integrating different parts of the energy system in the way you just described, where maybe we are electrolyzing water to get some hydrogen for the fuel sector, something that we could stockpile that hydrogen easily, turn those things off when demand spikes and resources drop. And that seems like a real option for trying to deal with some of this variability. I agree. Yeah. Yeah, well, they seem like the ones that could actually scale the best. So we're not going to get all of our electricity from hydroelectricity in this country. So these are the ones that are increasingly affordable and the ones that seem to be getting most of the hype. So that's why we looked at it for this study. All right. Oh, like shifting our times, doing away with daylight savings or something? Yeah, I'm only vaguely aware of that debate. Maybe we should talk afterwards. Maybe, I don't know. So there's another panel from our paper. So if you believe me that these shortfalls are going to need some flexible generation, perhaps, we start to think about, well, why can't we get some non-emitting generation to fill us in? And the thing to realize is that if we have 90%, let's say in some of my scenarios, 90% of our electricity being met by variable renewables, then that means just by definition that whatever we're getting the other 10% is only running 10% of the time. And most people don't want to build capital-intensive assets and operate them 10% of the time. This is why the integration idea starts to make a lot of sense. Right now, we're filling a lot of those gaps in places like California with natural gas, right? Combined cycle turbine plants. So those purple dots down here are the natural gas, and this is showing you the relationship of variable costs on the x-axis and fixed costs, so capital costs, on that y-axis. And the reason that that's important is that when you're talking about something that has a very low capacity factor, low utilization rate, it's all the more important that you have low fixed costs. You might be able to afford something with a high variable cost that's only getting charged that 10% of the time that you're running it, but you don't want to pay a lot for something to just sit there. And so the economics are really challenging because if you look at this plot and you see what are those generating assets that can provide us with electricity in a flexible way without emitting CO2, you'll notice that pretty much all of them have relatively high fixed costs compared to natural gas. So this is, I think of this as kind of one of the fundamental challenges of a reliable electricity sector is how do we come up with something with the economic characteristics of natural gas dominated by variable costs so we don't care if it's idle a lot of the time, but doesn't emit CO2. And I think this is where hydrogen power to gas to power ideas start to look really attractive because we can build these turbines pretty cheaply and a lot of the costs will be variable. So also looking at storage, this plot to me tells us a lot about why those gaps are tough to meet. Again, if you're only having these gaps 10 or less % of the time, you're not going to be cycling whatever storage very often. So here, if you're cycling something daily throughout the year, lithium ion is actually relatively cheap. But if you're down to where you're only cycling it on a weekly basis or less, you see that the prices of those things start to ramp up because of the capital costs that are involved. So just for sake of comparison, that's sort of where current natural gas generation prices fall. And you can see that if we're really only depending on this to back us up in those rare times when the sun and the wind aren't able to meet our demand, we're going to be dealing with really expensive relative to natural gas. Interestingly, and this gets to the hydrogen point, hydrogen, if we could get those electrolysis costs down, so this is where we are right now with electrolysis, about $5 a kilogram. If we could get them down to $1.50, so where reformed natural gas prices are today, we can see that even cycling rarely, we're starting to be a lot more competitive than, say, these green curves of lithium-ion batteries, or even the blue curve of pumped storage. All right, so just to round this out, given those low capacity factors, we already kind of said, anticipated by a question, integrating different parts of the electricity and energy system are really important. And so I've added on here a plant that maybe could burn hydrogen or synthetic hydrocarbon gas. And the idea here is maybe we're using excess electricity to electrolyze hydrogen and most times sending it to the transport sector. But when we don't need to or we have some shortfall in our variable electricity generation, we could then feed it back into a facility that could burn it and generate electricity. And by integrating those two things, we might be able to boost utilization rates and afford all of this. So to summarize for you, I've talked about these physical and techno-economic characteristics that make this net zero emissions energy system challenging. focusing on those three domains of aviation and long-distance transport, industrial materials, and highly reliable electricity. For the first, the long-distance transport, I've argued that I think we're going to need energy-dense liquid fuels for the conceivable future, and those could come from biofuels. We could synthesize zero carbon, zero emissions hydrocarbons, maybe ammonia, maybe direct solar fuels. And finally, I've said that to achieve this high reliability in the power sector, if we're assuming we're going to have a large share of variable, uncertain renewables, we need storage or flexible generation that has low fixed costs because they're only going to be running some of the time, and or we might be able to integrate different parts of the energy system, so have the same infrastructure generating products that could be used by different parts of the energy system. And so, again, I think electrolysis may be really central to a lot of these integration approaches because hydrogen is so valuable for both fuel making as well as you can burn it in a turbine. So with that, thank you for your attention, and I'm happy to take any questions.
Excellent talk. Really impressive work.
Thanks.
Super awesome. Where does livestock fit in with all this? Where does diet fit in with all this? That's another one to me that seems hard because I like hamburgers.
Yeah. Something I didn't emphasize in here, but we talk about in the paper, is carbon management. Because I think for non-point source land use change, agricultural emissions, I'm with you. I think it's super hard. This paper was all about the energy system, but I think going forward, it's pretty obvious to me that we're going to need to be managing carbon actively. So maybe that's direct air capture, which was on my schematic, and we're having negative emissions to compensate. Maybe it's CCS somehow, and we're actually burning biomass and sequestering, so negative emissions like that. There's other ways, but yeah, I don't see a future where we completely get rid of greenhouse gas emissions, and that's why I think, actually, believe it or not, some of these energy systems are easier to get rid of the emissions than livestock and some others. So if we think we want to stabilize the climate and get to the near zero emissions, probably this stuff, even the stuff I said was hard, is easier than some of the other outside the energy system. So, yeah. Sure. Well, so on the natural sources or the unintended sources of CO2, I think we had those things in the pre-industrial era too. It's this is a stock and flow issue. There's natural uptake of CO2 as well, and the ocean has been helping us out in a major way for a long time. So that's part of the reason we wanted to do those models where we artificially set emissions at different levels and saw, like, what does that mean for the equilibrium temperature change, because there will be some uptake and perhaps enhanced uptake by the biosphere in a situation where there's carbon in the atmosphere or ongoing emissions. So it's still, to me, a little bit of a question. That's not a fully baked project that I was showing plots from to figure out, like, how near zero do we actually need to be. I think it's very low is what I've been convinced of by the work we've done, but I don't know exactly yet how the natural systems may be able to increase their uptake and balance us out and stabilize the climate. Oh, we can talk about my professional trajectory maybe at the end. Is that?
So, like the whole decarbonization all the most expensive carbon emitting sources to move away from. And we do have some of these like natural ways of capturing carbon. So, what do you think will be the last thing, the things that we may never fully decarbonize because they'll just be too expensive and they won't be that good a
that was sort of the framing of this work, was like, what are the sort of last phase, the last 20%? We actually, so this says it, but we had a meeting in Aspen a couple summers ago, and we convened a bunch of people who knew a lot more than I do about different components of these technologies and systems. And that was the framing of that meeting, was what's the last 20% that we're going to decarbonize? And so, last 5%? Yeah.
5% that just may
Yeah, I mean, honestly, I think those industrial materials, CCS, if it's affordable, is going to be an option. But to actually change those underlying processes, I'm a little suspicious that that's going to be affordable. And because of the conservatism of the industries, that plays in as well. So it's not strictly a cost issue, but if I had to guess what's the last thing we're going to fundamentally change the process to decarbonize, it might be some of those. Back to the important stuff, sorry.
I'm curious, did you expect it to get that much press? How did you guys deal with it? And how does it fit into your larger hearts?
Yeah, so a lot of these questions that you're asking have been ones I've been asking myself in the last week that this has really hit, because I'm a beer lover, I have to admit, Judge Kavanaugh aside, and I brew beer at home, and so for me it was kind of a nice combo of my personal and professional lives, like, hey, well, this will be fun, but yeah, it's caught fire in a way that I didn't necessarily expect. I knew it would be sort of climate clickbait and that a lot of people would go after, but I didn't realize the magnitude of it. So that said, it has made me think, in talking to journalists about it, there's a lot of reactions. There's humor is always there, but then there's people asking, well, is there anything serious here? Or, and it's hard because you're walking this tightrope of there's existential threats from climate change and we're worried about beer prices, right? But so I've tried to rationalize and say something, it seems like where you're headed, which is for an affluent American who lives in Illinois, far from hurricanes and sea level rise, what do they care about that actually climate change is going to affect? And I think it's easy for them to sort of write it off like, oh, that's people near the coast in Bangladesh that are going to suffer, and I don't need to worry. I have my HBO and Chicken McNuggets, right? So maybe that's an angle, is to actually identify some impacts that are unexpected, like prices of beer, that maybe they would care about. I don't know if I'm going to pursue this as a PR campaign. I doubt we'll ever do any more work on beer. But I think it has been interesting, and I don't know. We'll have to kind of wait and see, I think, is the only way to know whether. I think conservatives are, for the most part, receiving this as these climate scientists are messing with us. So I don't know how seriously others are. I don't think anyone's changing their views on climate change because of this, at least. It doesn't seem to be. But, yeah. Yeah, it's interesting. So I think that has been the case for a lot of the media attention. People have just taken one conclusion, which is in the RCP 8.5, so the very high warming scenario, we saw prices on average would double in these extreme years. So that's the other thing that a lot of people miss, that we're talking about extreme events, not just the average. Anyway, a lot of the media attention that we've gotten, that's the headline, beer prices to double. And so it's interesting to me that people have kind of just absorbed that. But there have been people that have already started to do what you said, parse and get into the details. So the Brewers Association, which I didn't know if this was even a thing, but this is an industry, consortium. And they have a chief economist who seems like a sensible guy. He got a PhD at Berkeley. Anyway, he's been saying, well, not to worry, barley agriculture is shifting, we can stockpile. He's throwing out all these ways around this that like our paper is overstating the risks. And so you're exactly right. Like people are going to pick it apart. And I think that's normal and probably good, right? So that's fine. But does that answer your question? Or? Yeah, it does. Okay. Kind of both, yeah. So, I don't know who was next, sorry, but maybe you, yeah. Yeah, it's a good question. So those estimates were based on a study that my co-author Nate Lewis did with a student at Caltech, Matt Shaner. And I'm trying to think, I think they did include some storage, but not necessarily the transmission piece of it or transport of the hydrogen. Something, though, to talk about, though, is that we have a lot of natural gas pipelines. And so I was mentioning this to Professor Kendall earlier, that at UCI, we're actually doing some electrolysis on campus and mixing it into the fuel stream of our power plant that burns natural gas. Very low concentrations, but there's some professors there that are excited about increasing that fraction and think we might ultimately get to relatively high fractions of hydrogen being mixed in. That's exciting in part because we can use the existing storage and pipeline infrastructure from natural gas, which is they've done back of envelopes to see like how much of capacity there is, and as you might expect, there's a lot just in the existing pipelines and storage facilities. So I'm not sure that would really be the linchpin in the economics of it. I think the electrolysis is the main part to worry about. But did you? Sure. Oh, okay. Sorry. So they looked at a range of different technologies. I don't think that they were exclusively looking at platinum ones. I think the PEM ones are platinum-based, but the sort of old-school alkaline ones are not. They're nickel, right? So I think those were the least cost, which are still alkaline. But less dynamic, so that's an issue for integrating we've been talking about. Sort of the best case right now, I think, yeah. Oh, so yeah, I can talk offline with you guys too about my career trajectory. I basically just follow what's interesting to me. And so I got my undergraduate degree at the University of Florida in political science and philosophy. I thought I wanted to be the president when I grew up. And I realized that no one was going to throw money at a philosopher. So I went to law school and I got a law degree. I learned a lot at the University of Virginia. But I thought I wanted to be an environmental lawyer. And that makes kind of some sense, I suppose. But I kind of found out there, I had the fortune of being a student of a guy who had been the general counsel at the EPA. And he sort of dissuaded me, actually, from the environmental track. And he said, you will end up being an administrative lawyer that will be the expert on Section 58Q of the Clean Air Act, and that'll be your career. And I was like, that doesn't sound very interesting to me. So I ended up kind of going to the dark side. I practiced corporate law in Silicon Valley for about 3 years, helping startup companies. But in the meantime, my wife started grad school at Stanford, and I would go pick her up every day. And I was like, man, that looks really sweet to like be in school. So before I got totally locked in to the money of being a lawyer, I bailed, and I don't know how I did it to this day, like convinced this guy at Stanford that I wanted to be a geologist. Yeah. I think he mostly just liked the idea that a lawyer would be working for him, honestly. But yeah, so I hadn't had chemistry since 10th grade, and I went in and took like the pre-med chemistry at Stanford, which is probably the hardest thing I've ever done in my life. I didn't do that well, but nonetheless, I managed to get my PhD in sort of the mountain building is what I was studying, so the age of the Rocky Mountains. But along the way, I realized that wasn't very policy relevant. And I was learning a lot about climate change, so I thought, man, I want to do something that can actually help decision making. So I started a nonprofit that did life cycle analysis, basically carbon footprinting of consumer goods, And my grand vision was it'll be a market mechanism. We'll put labels on everything, and then when I go to the store, I can choose the lower carbon one. Well, I found out that data quality is an issue, especially when you're trying to compare, substitutable products. So one thing led to the next. I managed to find a guy at Carnegie, which is on Stanford's campus, Ken Caldera, who I was trying to get him to be on the board of this NGO, and he was like, okay, that's not that interesting, but what about if we did some work, you could come and do a postdoc, and we could look at this carbon embodied in global trade. And so I was like, wow, that's something pretty interesting. So I was meant to be a very short-term postdoc of his, but one thing led to the next, and we had a string of papers that were really, I thought, interesting, and were ultimately good enough to get me a job doing this at UC Irvine. So that's sort of the track, but it's much less like a planned trajectory than just like a trial and error type thing. And so I think, follow the things that are interesting to you and have faith that you'll land in a good place is maybe the takeaway.